Good morning, everyone. My name is Dhwani Gangal. I'm a PhD candidate at the Department of Physics, MNIT Jaipur. Today, I'm here to present my recent work on statistical signatures of non-classical Inflaton dynamics, Mendel's Q parameter in coherent squeezed number state. So this study probes the quantum statistical behavior of the Inflaton field by employing tools from quantum optics within the framework of semiclassical gravity. Here is the outline of my presentation. Firstly, I want to introduce about my work. Secondly, literature review. Third is what is the Mendel's Q parameter, why I'm doing this, and what are the formulation of Coherent squeezed number state in semi-classical theory of gravity. Next, results and conclusion. Publications which this paper is related to, and references which I have used. So in the introduction part, I want to investigate the behavior of the inflaton field in the early universe by modeling it at a quantum scalar field evolving in a flat FRW space-time. While standard cosmological inflationary models treat the inflaton classically, a full understanding of particle production and fluctuations spectra necessitates a quantum field theoretical treatment. So we employ non-classical quantum states. So we employ the non-classical quantum states, particularly coherent space number state, to study the statistical features of the particle production using cosmological's Mendel's Q parameter as our diagnostic tool. Secondly, in the literature review, this is the Einstein field equation that we can describe G mu mu is equal to 8 pi G T mu mu. Here that G mu mu shows the geometry of the curved space time, and T mu mu represent the energy content. And this is the CMB radiations, and that quantum fluctuations and the density fluctuation, we can understand the cosmic microwave background radiation. In the energy momentum tensor in the semi-classical gravity, we shows that ds square is equal to that curved space-time metric. We can represent ds square is equal to minus dr4. That is our time component, and the other three r1, r2, r3 are the position, or we can say the displacement component. So, uh, in the literature review, that several studies have implemented the quantum optical states like coherent squeeze vacuum state and coherent squeeze number state. So these states are highly relevant due to their enhanced quantum fluctuation and entanglement characteristics, making them suitable for modeling the pre-thermalization, or we can say that rethermalization of quantum phase post-inflation. So our work extends this by analyzing the behavior of coherent squeeze number state in incorporate where both displacement, that we can say a coherent component, and squeezing non-classical fluctuations. So in theoretical framework, we can see these equations. We consider a real scalar inflaton field, phi t with mass and spatially flat FRW background metric that we can describe by equation number 3. So here GT is the scale factor which shows us that how universe is expanding, how amount the universe is expanding. So that equation of motion is described by equation number 5, which shows the kg equation in the expanding background universe. We quantize phi canonically, introduce conjugate momentum. That equation number shows the conjugate position and conjugate momenta, and that equation number 7 shows the Hamiltonian, which is the combination of kinetic energy and potential energy. We have seen that literature review. So now we can say that formulation, how I formulate the squeeze coherent squeeze number state. So in this, we are using the creation and annihilation operator for the formulation. So here d gamma is the displacement operator. If we combine that displacement operator from the annihilation operator and creation operator, so we find the relation 11 and 12. And here we are using the three parameters that are coherent parameter. We can represent it by gamma, and squeezing parameter, so we can show it by row parameter and number parameter. So by using number operator, we are formulate the coherent squeeze number state under the FRW metric. So this is the formulation, and this we can say that this is the formula of Mendel's Q parameter. So in Mendel's Q parameter, we are using number state. So the equation number 15 will show the basic equation of Mendel's Q parameter. So Mendel's Q parameter measures the derivations from Poissonian statistics in the number distribution. Here, NT is the that number operator is the cosmological number operator. So by the values of Q, we can identify either our state is classical or either our state is non-classical. We can see quantum state. In this slide, I will show you that if the Mendel's Q parameter value is 0, Q is equal to 0. So we can demonstrate that we are using Poisson state. If the Q is less than 0, we will say that our state is no, sub-Poissonian. And if Q is greater than 0, so we can say that our state is super-Poissonian. So we evaluate Q, Mendel's Q parameter using the normal ordered second momentum of the number operator built from creation and annihilation operators expressed in terms of phi and pi. Here phi is our conjugate position, and pi is our conjugate momentum. So equation number 19 will show or captures the non-classicality signatures through high order quantum statistical momentum. So this is the in our equation we need e dagger square e square to compute the values of these three parameters. So firstly, I have computed this e dagger square e square for coherent squeeze number state. So here we get this big equation, and in this I'm using coherent parameter and squeezing parameter and number parameter. So in equation number 22, I'm computing that value of E dagger E for coherent squeeze number state, and in equation number next 24, this is the coherent Mendel's Q parameter for coherent squeeze number state. So by this big equation, we will identify the results and conclusions. Before that, I want to show you the tables and the variations with the values of rho, that is a squeezing parameter. So if we will change the values of rho, the row can take any value less than 0, greater than 0, less than 0, and by the varying the parameter delta t. So delta t can be anything, but we are ranging it from 0.1 to 5. So we can say that the Q parameter value will be positive. So positive value will show that our state is sub-Poissonian state or super-Poissonian state. So we will identify it which state we are using. So in this graph, we can say that in first graph that delta t value is 0.1. This is the graphical representation of the previous table. And in second, the delta t is 0.2, and further that we are taking the delta t is equal to 4 or 5 we can take. So it will show the dependence of Mendel's Q parameter with the squeezing parameter and the number parameter. So we can say that all the values are positive, and it will show the increasing curve. So here is it is the 3D graph. So 3D graph will show 3D graph will show that by the varying of t parameter, that is time parameter, number parameter, and squeezing parameter, it will reveal the non-linear amplification of quantum statistical fluctuation with squeezing and evolution time, yeah, time evolution. So this is the 3D representation, and we can take the whatever we want, the n value. So we are taking n is equal to 1 to 5. So that different values of rho and t and n, we will get the different Mendel's Q parameter for coherent squeeze number state. So here it is the graph for n is equal to 2, n is equal to 3, 4, and 5. And here in this graph, if we vary the rho parameter, like in first graph, the rho is less than 1. So we are taking rho is equal to 0.001. In next graph, we are taking rho is less than 1. So we are taking rho is equal to 0.01. And in next rho is less than 1. So we are taking rho is equal to 0.1. And in next graph, rho is 1. So we can say that we can take the any value of rho less than 1 to less than 1, or rho is equal to 1. So in this 2D graph, if we plot the graph between delta t and q CSNS, we will get the different values of Mendel's Q parameter. So here is the results and the conclusion of the result and conclusion of this presentation. So in results and conclusion, firstly I want to show you that we are getting the Mendel's Q parameter values greater than 0. So we can say that our state or this presentation is increase indicating the super-Poissonian statistics. The dependence on rho becomes significant when rho is greater than 1, indicating strong squeezing effects dominate non-classicality. So we can say that we are doing the quantum treatment of this state. So for small rho values, Q varies mildly with delta t is equal to t minus t naught. And for large rho, we observe rapid growth in Mendel's Q parameter with time. So we can say that for small values of rho, it will show more contribution in the Mendel's Q parameter. So in next point, for gamma is equal to 0 and n is equal to 0, it will convert to squeeze vacuum state. For that, we will get the Mendel's Q parameter Q CSNS less than 0. So we can say that it will consistent with the sub-Poissonian behavior. So, in the conclusion part, we can say that we have formulated a cosmological analog of a Mendel's Q parameter and applied it to CSNS, or we can say that coherent space number state. The Inflaton field exhibits the strong non-classical behavior, particularly of super-Poissonian type squeeze number state. Our analysis provides a quantitative measure of the quantum fluctuations in the Inflaton field particle production. And at last, this framework can be extended to study perturbations, decoherence in the early universe of the cosmology. So, this presentation is related to these two publications, which are published in IGTP and IGMPA. And these are two more publications which I have published during my research work. And these are the references which I have used to make this presentation. And thank you so much.